The next layer of the sun that we're going to talk about is called the corona. Now, corona means crown. And if you have ever enjoyed a Corona beer, you may or may not have noticed a small crown on that emblem. The corona is the outermost part of the solar atmosphere. It is basically the source of our solar wind. We cannot see the corona with our naked eye. During an eclipse, the corona is this white, beautiful white halo that actually surrounds our star. Now, do you remember, just see if you can recall this from things we've done in the past, what do you call the pink layer? Okay, the pink layer is the chromosphere. Chromos means color, so the pink is the colored layer, and the corona is the white part of the gases emitted by our star. When you look at a picture of the corona, notice something. It is very, very dense. These gases are dense near the surface, and then they spew outward. Now, this goes in 360 degrees all the way around the star. And as they travel further and further out, the density of these gases gets less and less and less. So it goes from an area of high concentration. So by the time you get here, it is very low concentration. By the time these gases get to our position past the Earth, the concentration is even less. But the corona is very visible during an eclipse, but I want you to understand it produces this solar wind that we can detect a long way away, even millions of miles away, where we happen to exist. The corona produces one of the most interesting mysteries we have in astronomy right now. And the mystery has to do with temperature. The hottest place in the entire solar system is the center of the sun. It's the nuclear furnace. It's millions of degrees Kelvin, and it's a really, really hot place. And as you go from the center of the sun outward, it's going to get cooler. It's sort of like if you walk further away from a bonfire, it's going to get cooler the further away you go. The challenge is, by the time you get to the surface of the sun, we're talking about something that is maybe 6,000 degrees Celsius at the photosphere. The corona, though, as you go further away, it's maybe 6,000 degrees at the photosphere, but the corona can be 1,000,000 degrees. So that's the big question. How do you get further and further away from the source of the heat and still get hotter? Scientists don't have an incredibly good answer for that yet. We're thinking about it. A lot of people are doing research in it. We suspect it might have something to do with the Earth's magnetic field. The sun's magnetic field, and that the sun's magnetic field may interfere with these high energy gases and actually accelerate them, make them move faster. And if you have a gas that is moving faster in the world of physics means hotter. So I love a good mystery, and hopefully we'll find out the answer to that one before we all get too old. I mentioned before that the corona is this extension of the gases emitted by our star that just keeps going further out into the solar system. And I know throughout the course I've talked about solar wind. That is that corona that has just been traveling for millions and millions of miles. It gets thinner the further it travels, and by the time it gets to our Earth, it gets trapped in our Van Allen belts and our magnetic field, oscillates back and forth, enters the Earth's atmosphere at the north and south magnetic poles, and gives rise, of course, to our auroras. But the coronal gases and the solar winds are going to extend millions and millions and millions of miles to the very edge of the solar system. There was a spacecraft launched back in the 1990s named Voyager, and as Voyager was shot out into space, it's been traveling for 40, 50 years now. And in that time, it has gone through what is referred to as the heliopause. Helio means sun, pause means to stop. And this is the place on the edge of our solar system where the solar wind can no longer be detected. Where is this? This is well past the orbits of Neptune and Pluto, and somewhere kind of on the edge of the Kuiper Belt. The solar wind gets thinner the further it travels, and it has gotten so thin that it's kind of petered out and spread out so it's not detectable uniquely as coming from our sun anymore. When you get beyond that solar wind, you are officially in interstellar space. So this little old Voyager spacecraft that's been traveling for 50 odd years It is officially an interstellar space, which is pretty nifty. The corona itself is made of charged particles, so protons, neutrons, electrons, and charged particles interact with magnetic fields. This is a lovely picture of a magnetic field. We've talked about these in the past. If you have a bar magnet, the ends of the bar magnet, the magnetic fields go straight up and down, and in the center, there are kind of round or circular contours to those magnetic field lines. Well, if you actually can see the corona carefully enough, you can actually get a decent picture of the sun's magnetic field. You can see the north and south solar poles, magnetic poles, and the coronal particulate gases are actually streaming out of the north and south poles. And if you look here, hopefully you can see the sort of rounded edge to this part of the corona. That is an indicator of the sun's magnetic field. So each layer of the sun gives us more information, and those pieces of information really have helped us construct a good picture of what's going on with our very hot, very nearby star. One of the other coronal features that we're going to look at when we look at various images of the sun are things that are called coronal holes. They're not actually holes, but they are cool and quiet regions of the sun. The sun has these convection currents where hot plasma is going up and going down. Where the plasma is coming up, it's going to be particularly hot. Where the plasma is going mostly down, that's areas that are going to be quite cool. And so if you look at a picture of the sun, these are going to appear blackish. If I could cut out one of these and paste it against the black of the night sky, it would look as bright as its own star. But we're looking through specific filters in order to see these coronal holes. And the other thing is, the only reason they appear dark is because they're totally surrounded by things that are just happen to be a couple thousand degrees Kelvin hotter. The coronal holes are a big source of our solar wind. A lot of solar wind is ejected from these coronal holes. And so if there are more coronal holes, it's an indicator to us that we are going to have more solar wind, and more solar wind means that we're going to have auroras and features as our planet interacts with the sun's solar wind. All right, folks, that's going to stop this section. Next time, we're going to come back and talk a little bit about sunspots.